Hello everyone and welcome back to A+ Physics. I'm Dan Fullerton, and in this lesson we're going to talk about vertical spring block oscillators. Our objectives include analyzing the motion of a vertically oriented spring block oscillator. And when we look at one of these, what we're going to do is we're going to start off with a very standard analysis of an oscillator. We've got a mass on a spring with some spring constant K, and we can displace it an amount equal to the amplitude A or negative A in either direction. We're defining down as our positive y direction. And we'll call this point where it settles out y, call that y equilibrium. So when we do this, we start our analysis by drawing a free body diagram for the block. So let me do that for a minute. And we're going to note here that gravity pulls the mass down, mg, while the force of the spring provides that upward force. So we'll call that one Fs. Excuse me. And by Hooke's law, the force of a spring, the magnitude of that is K times its displacement, the spring constant times its displacement. So at its equilibrium position, we know y equals y equilibrium, so we can write a Newton's second law equation in the y direction to analyze what's going on. The net force in the y direction is equal to, well, we have mg down minus ky, because that's up in our negative y direction. All right, and that must be equal to mass times acceleration in the y direction by Newton's second law. So what we can do now is, recognizing it's at equilibrium when it's at this y equals y equilibrium point, when it's settled out, at that specific point then, the acceleration is 0. It's just sitting there. So mg minus ky equals 0. Therefore, at equilibrium, solving for y at that equilibrium position is equal to just mg over k. All right, great. And once the system has settled at equilibrium, let's say we displace the mass by pulling it down some amount, either plus a down or minus a up, and then letting it go to see what happens as it oscillates about that point. We can then analyze this new system as follows. Well, now the net force in the y direction is mg down, gravity hasn't changed, the force of gravity on our object, minus k, and our displacement now is y equilibrium plus that amplitude a, which implies then that mg minus k y equilibrium minus ka, when we go through and we multiply our k through, well, that is still equal to all of these, equals our F net, our net force, and that's net force in the y direction. But now if we look up here, we already know that mg minus ky at equilibrium equals 0. Well, if we have mg minus ky equilibrium equals 0 up there, we can replace mg minus ky equilibrium down there with 0. Therefore, what we come up with is that the net force in the y direction is just equal to minus ka, minus k times that amplitude, times that displacement. So what we're really saying then, in this case, is that when we do this, we can treat it as if it's a horizontal spring block oscillator that's just oscillating around that center point, that equilibrium point, and treat it just the same way. We don't have to worry about all these extra things. That's maybe a little bit easier to see when we do some demonstrations. So let's start with a couple demonstrations, and then we'll do a couple problems. All right, for our first demonstration, we'll take a look at our vertical spring oscillator over here. In this case, we have a 200-gram spring block oscillator, 200-gram mass, and we're going to displace it an amount, an amplitude, of 6 centimeters from its equilibrium position. Well, we know that we can solve for the period using t equals 2 pi square root m over k, which should be 2 pi times the square root of our mass, 0.2 kilograms, over our k, and for this spring, it's 16.3 newtons per meter, gives us about 0.696 seconds for the period. So as we displace it here, as you look at that, we'll displace it, you will see that it's going up and down 6 centimeters from that equilibrium position. And we can actually count and look at the period as well. If we look for 10 revolutions, well, as we watch here, for 10 revolutions, it's going to take us about 7 seconds. So we have 7 seconds for 10 revolutions, or 10 cycles. So our period then, the time for one cycle, is 0.7 seconds experimentally, which matches up very nicely with what we just found theoretically. Let's put a different mass on our spring. Let's go to our next demo page here, and now we're going to make this 250 grams. We'll still displace it by 6 centimeters, and we'll see it oscillate about that center point, 6 centimeters in each direction, about that equilibrium position. And we can calculate the period. Theoretically, it should be 2 pi square root m over k again, which is 2 pi square root of our mass, 0.25 kilograms now. Same spring, so k is still 16.3 newtons per meter. And I come up with about 0.778 seconds. So let's do it. And as we watch here, we'll watch 10 cycles of our spring going up and down. And as I time that, I find that it takes us, for 10 cycles, it takes us about 7.8 seconds. So our period then, the time for one cycle, one complete up and down trip back to where you start, would be 0.78 seconds. Matches up very nicely with what we found theoretically. All right, let's do this one more time. Now, when we look at this one, we're going to put a 300 gram mass on the end of our spring. Again, we'll displace it 6 centimeters, and we'll watch it oscillate back and forth 6 centimeters up and down from that equilibrium position. Theoretically, as we calculate our period, that's still 2 pi square root m over k, which will be 2 pi square root 0.3 kilograms over 16.3 newtons per meter. And I come up with a theoretical period of about 0.852 seconds. Now let's actually do it and check it out. All right, as we watch it go here, we're going to watch 10 cycles. So for 10 cycles, I come up with the time, as we look at the movie over there, of about 8.5 seconds, which means the period is about 0.85 seconds for each one of those cycles, which again matches up very well with what we understand for our theoretical answer. All right, so it works pretty well from that perspective. But now let's do a couple problems where we're doing some deeper calculations instead of just some demos. So let's take a look here. A 2 kilogram block attached to an unstretched spring of spring constant k equals 200 newtons per meter, as shown over here in our diagram, is released from rest. Determine the period of the block's oscillation. Well, that goes right to our period equation. Period of a spring, 2 pi square root m over k, which is 2 pi times the square root. It's a 2 kilogram block over our spring constant, 200 newtons per meter. So the square root of 1 over 100, which is going to be 1/10 of 2 pi, or 0.63 seconds. All right, not too bad there. Let's do one that's a little bit more involved. Now we've got our 2 kilogram block attached to that 200 newton per meter spring, but we're going to take it a little bit further. What is the maximum displacement of the block from equilibrium while undergoing simple harmonic motion? Well, the gravitational potential energy at the block's starting point, mg delta y, must equal the elastic potential energy stored in the spring at its lowest point. So we can use this to solve for delta y. So the gravitational potential energy, Ug, must equal the stored potential energy in that spring, which implies then that mg delta y must equal 1/2 k times the displacement squared. Therefore, solving for delta y, we come up with 2 mg over k. And if delta y is the total displacement of the block from its highest point to its lowest point, well, the maximum displacement of the block from its equilibrium point, a, must be half of that delta y. So a equals delta y over 2, which is mg over k, or 2 kilograms, times acceleration due to gravity, 9.8 meters per second squared, all over 200 newtons per meter, which is going to be 0.1 meter. So that's how much it's going to stretch in one direction. All right, so we took this now, we had our spring, and then we dropped it, and we were able to calculate how far it's going to fall. Okay, let's do another one. A 5 kilogram block is attached to a vertical spring of spring constant 500 newtons per meter. After it comes to rest, it's pulled down 3 centimeters and released. What's the period of oscillation? Well, first we determine the displacement of the spring when the block is hanging and at rest. Now, to find the period of oscillation, we don't have to do a whole lot. This we can just use our same formula. Period of the spring is going to be 2 pi square root of m over k again, which is 2 pi square root of 5 kilograms over 500 newtons per meter. Again, 5 over 500, 1/100th, square root of that, 1/10, so 1/10 of 2 pi will be 0.63 seconds. But if we now take this a little bit further, we think about what happens when we pull it down 3 centimeters and release it, we can determine the displacement of the spring first when it's hanging and at rest. So let's do that for our next example. When that's the case, the net force in the y direction has to be equal to 0. It's not accelerating, it's in equilibrium, which implies that k times its maximum displacement, we'll call that d, must be equal to the force of gravity on it. The force up must be equal to our force down. Therefore, that displacement d must be equal to mg over k. We've got our mass, 5 kilograms, our acceleration due to gravity here on the surface of Earth, 9.8 meters per second squared, divided by k, 500 newtons per meter. 1/100th of 9.8.098, or close enough to call that 0.1 meter. So there's our resting position. Now, however, the block is pulled down 3 centimeters, and then we're going to release it. So the maximum displacement must be the displacement while the block is at rest, in addition to the 3 centimeters we pull it down. So the maximum displacement, y max, is its hanging rest position, which we just found, plus that 3 centimeters, 0.03 meters, or 0.13 meters. And as I think you're probably seeing as we go through these problems, it's very much about how you read the problems and interpret them. Take your time reading the problems and really figure out what they're trying to say, what they're asking you. Because they can change just a few words and mix up the problem with what they're asking for quite a bit. So the concept's pretty straightforward. Interpreting the question is where most troubles come in. All right, thank you so much for watching. Hope this gave you a great start on vertical spring block oscillators. If you need more help or looking for more information, you can find tons of extra help on the A+ Physics site and the various associated sites. Thank you so much for your time, and make it a great day, everyone.